Hello everyone, I'm great to share some of the work by our team on HackinAbout. Today, we will share some of the security research findings of LPWAN, insecure link, security analysis and critical attacks of LPWAN. First of all, please allow us to introduce ourselves. I'm Li Yuxiang. I'm a senior security researcher at Tencent Blade Team. Now, I am focusing on mobile security and IoT security. I have also reported multiple vulnerabilities in Chrome and Android, and I am also a speaker of BlackHat DevCon, Kenzie West, HackinAbout. The other is my teammate, HuiYu. He is also a senior security researcher at Tencent Blade Team. Now, he is mainly focusing on IoT security research. He is also a bug hunter, winner of GitPwn, and speaker of BlackHat DevCon, HackinAbout, Kenzie West, and POC. Tencent Blade Team was founded by Tencent Security Platform Department, focusing on security research in the areas of AIoT and cloud visualization. Report 200 vulnerabilities to vendors such as Google, Apple, Microsoft, Amazon. For more detail about our team, you can visit our team website. Let's take a look at the agendas. First of all, we will introduce the basic knowledge of LPWAN, related supply chains, and the difference between LoRaWAN and NBLT. In the second part, we will introduce the new findings of LoRaWAN security research, LoRaDAM, as well as our practice. The third part will share the internal implementations of MBLT chip and security risk. Finally, we will provide some security advice to the relevant vendors in the LoRaWAN and MBLT supply chain. In order to overcome the limitations of soft-rank protocol, low-power wide area networks LPWAN was introduced, which offers a long-range connectivity in the orders of kilometers. It has low power and low bit rate for long-distance communication. The mainstream LPWAN technology include LoRa, MBLT, SIG4. At present, these communications technologies has been widely used, including smart city, smart architecture, smart industries, and so on, which belong to the application scenarios of LPWAN. Why did we choose to study the security of LPWAN? According to the research of some organizations, it is predicted that more than 1 billion devices will use LPWAN technology in the future, among which LoRa and MBLT will occupy a large market share. At the same time, compared with ZigBee, Bluetooth, and other communication technologies, the security research of LPWAN is relatively less. With the large-scale use of LPWAN devices, security in this area will be very important. Okay, let's introduce the two mainstream technologies involved in this topic. LoRaWAN and MBLT. First introduce LoRaWAN. LoRa is a modulation technology used in the physical laser that enables long-range, low-power communication by using CSS modulation. It uses unlicensed frequency band. Anyone can independently deploy the network. LoRaWAN is a cloud-based media access control laser protocol, but acts mainly as network laser protocol for managing communication between LPWAN gateways and end node devices as a routing protocol, managed by the LoRa Alliance. MBLT is a new IoT technology set up by 3GPP as a part of Release 13. Although it is integrated into the LTE standard, it can be regarded as the new air interface. It uses the lion's frequency bands, which are the same frequency numbers used in LTE, and employ QPSK modulation. There are different frequency band deployments, which are standalone, guardband, and in-band deployment. Let's take a look at the supply chains in LoRaWAN and NB-IoT in the real world. Let's start with the chip. LoRa patent technology is dominated, mainly concentrated in Zen-Touch. There are more MBLT chip vendors, including Qualcomm, MediaTek, and HiSilicon, all of which has deployed development chips of their own architectures. Then there is a model. Some major models manufacturers such as IK, Cortex, Blacks, encapsulate the chips and the capabilities they provide through integration and give them to the equipment manufacturers. Equipment manufacturers will purchase a large number of models for the development of end products. For example, water and electricity meters, dock, window sensors, and so on. In the end, when deploying the LPWAN solution, you need to work with cloud vendors or operators to complete the deployment. At this point, the whole solution is fully deployed, and the schemes will be managed or optimized with cloud data in the later stage. We find that in the real world, a complete LP1 solutions require the participation of many vendors, so we think that the security of LP1 supply chains is worth studying. Let's briefly compare the difference between LoRaWAN and NBLT. From the technological characteristics, because LoRaWAN is simply and easy to deploy, so in better life coverage, cost efficiencies will be better than NBLT. On the concentrates, NBLT is measured by traditional telecom operators and refer to 3GPP standard, so it is excellent in terms of latency and security. Security is the focus of our presentation. LoRaWAN uses AES 1S is security-based. MBLT is secure features for LTE, which has security protections in AS and AS. At the same time, it uses SIM cards as authentication, which is relatively more secure. Let's take a look at the difference between the two technologies in network architectures. First, the LoRaWAN device transmits data to the gateway by radio. The gateway is very similar to the router. One side receives LoRa packets. The other side can access Ethernet through LTE, Wi-Fi, and other way. Finally, it reaches the network server, and the solution managers can manage the device according to the application servers. The LoRaWAN gateway is easy to buy, which is of great help of our security research. MBLT is quite different. It is a modified version of LTE. Therefore, the device is connected to the operator's networks through the base station, called eNode B in LTE. An eNode B is expensive and difficult to buy, and require in-depth knowledge of radio before it can be deployed on its own. Then, there is a core network server of operators. MBLT follows LTE's EPC, which is a complete black box for Earth. Finally, connect to the IoT platform through the network. Manager can manage the equipment through this platform. Next, let's take a look at the LoRaWAN protocol. The whole protocol consists of two parts. The LoRa is responsible for radio modulation and demodulation. The MAC laser is our focus. According to the specification, LoRaWAN devices will be divided into three categories: Class 1, Class B, Class C. Choose according to different scenarios. There are many keys in LoRaWAN. Generally speaking, the security basics of the protocol is AES. The app key is stored in the nodes and servers, used to generate the season key. Network season key and application season key are season keys that are used for encryption, decryption, and MIC verification. LoRaWAN has two ways to active devices, ABP and OTAA. ABP can be understood as a const season key, while OTAA conducts key negotiation through APP keys. The existing security studies of the two technologies are mainly as follows. For LoRaWAN, the existing security issues are mainly protocol specifications and key deployment. The security issues of the specifications, which has been fixed in the new version of the specification. But there are also great challenges in using the new specification in the real world. The security risk of LoRaWAN deployment is usually issues of security use of keys. At this stage, it can be well served by improving manufacturers' security awareness and compliance operation. As for MBLT, there are few studies, most of which is surveys of theory. We will not introduce the security risks of the protocol specification in detail. Let's take a look at the security states of LoRaWAN devices in the real world. After our analysis, it is generally divided into two types of vendors. One type of vendor is already aware of the security risk associated with nodes deployment. Every key is usually a random key or one machine one key, which great guarantees the security risk of the network. In addition, they also provide guidance of hardware security. A types of vendors still lack security awareness. In order to facilitate deployment, they usually use the same app key or a well-known app key, or marks the app keys on the device shells in plain text or serial code. At the same time, there is not enough attention to the protections of hardware and firmware. We believe that if more and more vendors pay attention to the security of LoRaWAN, these problems will be solved. So, besides these security risks, what other LoRaWAN security issues has not received enough attention? Now, we will introduce our new discoveries in the LoRaWAN supply chain, namely LoRaDAM. This is a security issue involving the supply chain, which has not received attention in previous studies. Their risk occurs in nodes, gateways, and cross servers. Next, we will introduce the implementations of the LoRaWAN supply chain and existing attack surface and our practice. LoRaWAN has many open source implementations. and these implementations are actually used in the real world. This slide lists several of the projects involved in our study, including the LoRaWAN protocol stack, gateways, and servers. These open source projects can help us better understanding the LoRaWAN solution. At the same time, it indicates a project that is being used in the real world. Let's take a look at the architectures of the LoRaWAN node. Products on the market usually have two architectures. The first is the MCU plus radio mode. This method is low cost, and the application and LoRaWAN protocol stacks runs in these MCUs and operate radios to send radio packets. The other is the ways of adding models to external MCU. At this point, MCU usually only run application or RTOS. The works on the protocol stacks and radio operation is integrated into the model, and the model vendors will also add the parts of the AT library. But regardless of the architecture, we find that the LoRaWAN protocol stack is an essential common component. The most widely used protocol stack is LoRaMAC node. This is why we started in this software. LoRaWAN gateways are similar to routers. Packet forwarder components are usually running on Linux. The packet forwarder component reads the LoRaWAN packet through the drivers. It encapsulates the data into the specific protocol and sends it to the network server. Packet forwarder components, including packet forwarder, basic station, MQTT, and so on. Hardware need to be connected to the SX1301 to operate LoRa radio packet. For example, the architectures of the RAK 831 gateway shows that it is based on Raspberry Pi connect to SX1301 through a Gauter spot. The mainstream LoRaWAN servers are CurbStack and TDN, both of which can be used for private deployment. In addition, TDN provides public service that allow anyone to build LoRaWAN solution. The two architectures are as follows: CurbStacks on the left and TDNs on the right. In general, they all include several components: MQTT brokers, network server, application server, database, interaction. Communication between these components use MQTT, gRPC, HTTP, and other protocols. After introducing the technology implementation in the real world, let's summarize the security risks of LoRaWAN supply chain. On the node, we can pay attention to the vulnerabilities of the LoRaMAC node, which is widely used software. On the gateway, we can pay attention to the security issues of different packet forwarders. On the server, they are all written in Golang, so we can focus on the security risk introduced by the default configuration and open source code. First of all, let's do the security analysis of LoRaMAC node. The software is developed by Tencent and is widely used. Most packet processing needs to know AES key, which we think will be very difficult in future. Therefore, our focus is on the logical before participating in the AES operation. And this part of the code is very simple, but fortunately, we found a vulnerability. The vulnerability is caused by LoRaMAC nodes fail to verify whether the packet length is valid when processing join accept response packet. The vulnerability exists in the process of OTAA, which can cause harm to the devices that are joining the network. For deploy projects, it is necessary to redrain the network, which need to be combined with other attack methods. The obvious advantage of this vulnerability is that we can launch attacks without losing the APP key and achieve a widespread denial of service by sending malicious radio packets. So, how do we send radio packets? Because of the low power consumptions of LPWAN, they are not always online. So, attacking such devices require a specific cycles. The receive windows of Class A devices is defined in the LoRaWAN specifications. After the device sending an uplink packet, two stop receiving windows will be opened, and the LoRa packet will be processed only when it is received in the receiving window. In addition, the downlink channel is also different in different areas. For example, in CN 470, RX1 channels number equals uplink channel number mod 48. Therefore, after calculating the appreciate, delete, and channel, you can really launch an attack. After having the ability to send malicious video packets, we can select some deployment boards as the environment for local LoRa node debugging. We can choose listed NUCLEOs LR1's deployment boards as the tax equipment, which provides MCU, expansion boards, and STIC link. VS Code and OpenOCD are used to debug the software. This development board is very suitable for debugging the protocol stack, can help us quickly verify the vulnerability. When everything was ready, we choose a temperature sensor as the target to check it. The attack flow is as follows. When the temperature sensor sends an uplink OTAA packet, our hijackers sniff the radio packet and notify the local server. After calculating the downlink channels and delete, the local server sends the malicious packet to the hijacker. The hijacker sends it to the device after an appreciate delete. At this point, the sensor receives malicious packet, triggers the related vulnerability, and the device denial of service. The above is the practice of the LoRa node vulnerabilities we found in the actual devices. We believe that LoRaWAN equipment is used very much and is mostly used in unattended scenarios, such as smart city and agriculture. Even denial of service has a great impact. Next, let's take a look at security of the gateway component. LoRa Basic Station. LoRa Basic Station is new state-of-the-art gateway packet forwarders compared with traditional components. It defines two protocols, CUPS and LNS. CUPS is used to upgrade basic station, and the protocol formats generally include length and data. LNS use WebSocket to establish a long connections with the server, and the servers can send data to the gateway. In theory, if TLS pending is used, it will be safer. After our analysis, we believe that there are many security risks in this component, which may lead to security risk under MITM hijacking of malicious servers. The main risks are as follows. First, this component does not enable authentication mode by default, so a lack of security awareness of the deployers may lead to MITM hijacking. Second, the LNS protocol contains powerful capability and may be at risk of a bust. The service is fully true in the LNS protocol. Therefore, even if TLS is enabled, a malicious server can still abuse the capabilities of the LNS protocol, such as the remote code exception. Third, CUPS itself has memory or logical vulnerabilities when processing the data, which can lead to security risk. Risks of abuse of LNS capability. We learned from the documentations that LNS contains remote commands. Also, it is helpful for remote managers of gateways. We believe that it may be above and lead to security risk. Therefore, we can RCE by hijacking of malicious server to send package to the gateway component. For example, in the pictures on the left, we create a plaintext pan.txt files on the gateway by the above LNS capability. Next, we will share the security risks of the servers. The default configurations of CrashDeck is a security risk. If the server deployer does not read the instructions carefully or does not have security awareness, it will lead to the risk of an attack on the server. For example, the default weak passwords may be used in the database web. If an attacker can enter the web service of the application servers with a weak password, we can obtain sensitive device information, such as device name, APP key, and so on. In addition, some MQTT and gRPC surveys are not authenticated, which can lead to permissions of data disclosure. We verified this security risk in April last year. A few days later, we researched the current networks and found that the deployment of CrashDeck servers shows a growing trend. These security risks are worth of our attention. MQTT integration is usually used by managers to manage the deploy LoRaWAN solution. In the default configuration of MQTT broker, the username, passwords, and ACLs are optional. Therefore, incorrect configurations may bring the following security risk. Attackers can subscribe to any topic through wildcards. In this way, the data of the interaction between the device and the servers can be obtained, including device information. After knowing the device information, the attacker can also forward downlink data and send it to the nodes through MQTT. In addition, we found a bug in the UDP parsing logicals of the LoRaWAN stack code. Sending a malicious UDP package caused the server to crash, when the gateway ID is null. There is also a way to attack the server. Because servers are deployed by Golang, memory vulnerabilities are rare, so you can pay attention to logical vulnerabilities. There may be some unexpected discoveries. After introducing the security risks of LoRaWAN supply chain, we will share some research findings about MBLT. Similarly, we will also introduce some of our current attempts in terms of technological implementation, attack surface analysis, and practice. Let's start with an overview of MBLT chips. MBLT chips are highly integrated URI SoC. It contains different chip architecture and RTOS. In addition, the MBLT protocol is far more complex than LoRaWAN. The entire protocol stack includes baseband, TCP/IP, and application. The baseband includes the physical layers of MBLT, and the upper layer follows the protocol of LTE. Finally, in the MBLT network, there are black boxes in the EPC MBLT cloud platform, which bring a lot of challenges to the security research. Next, we will introduce some findings in the reserve engineering of MBLT chip. We will introduce chips from two mainstream manufacturers. Next, we will introduce two MBLT chip architectures. First of all, let's introduce the chip architectures of A. It is a multiple-core architecture, each core using ARM Cortex-M0. The three cores are used for different purposes, and each core has its own RTOS for task scheduling. Core A contains the application layer protocols in the TCP/IP protocol stack, such as DTLS, CLAP, LWM2M. In addition, it also includes the application layer, which is used to provide model vendors to deploy developers the corresponding IT libraries of application development. APPs can only provide IT commands interface so that external MCU can interact with MBLT chip of models directly through AT command. In this way, the development of the application is mainly focused on the external MCU. Core B mainly deal with low-level protocol, including baseband, such as NAS, RC, L2, L1, related to MBLT. The use LWIP as the TCP/IP protocol stack to provide socket wrappers function for Core A. Core C is mainly to provide some security capabilities, including the security checked needs by security boot, FOTA, and so on. The manufacturer involves a set of RPC mechanisms which use shared memory to realize the interworking of data between cores. The other chip architecture is explained in a single-core way. Take chip B as an example, which uses ARM Cortex-M4. The entire core is divided into two domains, including the application domain and model domain. It is very similar to the divisions of AP and modems in mobile phone. Each domain use a different RTOS for task scheduling. The application domain includes the entire TCP/IP protocol stack and the upper application. Compared with Shift A, it also used the LWIP libraries as the TCP/IP protocol stack implementation, but it belonged to the application domains together with the upper layer protocol. Modern domain is mainly related to baseband processing. The two domains communicate with each other by shared queue. Bootloader is also included in this course. Similarly, the app layer in the application domain can provide only the AT command interface for external MCU to operate through the AT command. After our result analysis, we found that even though different vendors adopt different architecture, but some technological implementations are similar. We summarize the attack surface of MBLT chip. There are three categories. The first category is related to TCP/IP, which may use the same surpass libraries or implement specific logic based on the standards. The other is related to baseband, where the technology implementation is related to chip vendors, each of which has its own implementations and will not use open source libraries. It's more difficult to find these kinds of software vulnerability. Another category is the risk of inter-cost communication and inter-domain communication. Most of the codes we mentioned belong to chip manufacturers. Model manufacturers mainly work in apps. In addition to the attack surface introduced here, the application processing logical display developed by the equipment manufacturers will also have security risk, but because the program developed by the equipment manufacturer is not a common component, we will not introduce it here. If you want to attack programs developed by equipment vendors, you can choose vendors with a high market share. Because the MBLT chip is highly integrated and the technology is broad, it is difficult for us to purchase the evolution boards of the chips for debugging. Therefore, we can only get the running status of the chip by log and debug it. Manufacturers has provided useful software to view logs. Through the log, we can see some output inside the chip, including the state of the baseband, the output of applications, and so on. It is a little helpful for us to understand the program flow and verify software vulnerability. So how do we send package to the MBLT chip? We made some attempts. Different testing tools are adopted according to different protocol stacks. If it is a TCP/IP related test, we use Raspberry Pi EC20 and IoT SIM card to access the network for testing. For baseband related tests, SDR and test SIM cards can be used for testing. We can use open source projects for testing, but the capability is not very good at present. At the same time, we can also buy a MBLT base station for testing, but it is not easy. There are still many challenges to overcome throughout the testing process. And if you have done similar work, you can also communicate with us. Okay, my part is over. The following time will be shared by my teammate HuiYu.
Thanks. I will continue to share the following part. In this part, I will provide some security suggestions about the LPWAN Blade Team. I hope this suggestion can help the vendors to improve their product security and can make a small contribution to the community of LPWAN. For LoRaWAN, we believe that node developers should use a latest version of protocol stack for development, and the development and deployment of gateways is needed to enable authentication and encryption mechanisms. And the service provider should clear the weak password, enable authentication, and validate the input data with the open port. For MBLT, we believe that the chip or model vendors should update third-party libraries or chip firmware in a timely manner. When using a CORP and MQTT as communication protocols, TLS and authentication should be adapted to improve security. In the part of EPC, operators should make a good network access policy to improve the security of the network. Okay, that's all. Thank you for your listening. And if you have any questions, you can connect us by this email.